Okay, today we're going to be doing a Fourier analysis. We have our Fourier equation right here, where we have f of t, it's for some time, is going to be equal to your initial value here, which we'll go over in a second, the sum of your a sub k coefficient multiplied by the cosines, and your sum of your b sub k coefficient multiplied by your sine waves. The Fourier series equation will essentially find the amplitude and frequency of each individual cosine and sine wave within a segmented function. For our example today, we're going to be going over a sawtooth function. A sawtooth basically works as little tiny teeth in between here that we'll see in the next MATLAB code, where the more data points and the more sinusoidal wave functions we have, the more they'll cancel each other out to equal certain functions. At 0 and 1 period, we have the waves canceling each other out, so we get an asymptote or a 0. And here is our line that we'll be solving for. This is our function of our sawtooth. The b sub k and a sub k coefficients are calculated by taking the integral of 1 period of the function for your specified equation or diagram multiplied by the sine of your kth variable multiplied by your angular frequency with respect to time. Your a variable calculates your cosine waves, and your b variable finds your sine waves. So as we determine what a and bk will be here, and we know that a is 0 here because the mean area of 1 period, the area above the curve, is equal to the area below the curve. So the mean area is going to be 0. Your a sub k variable is going to be solved with an integration by parts. We have our known variables taken out, and we're left with a t multiplied by a cosine of t. So it's an integration by parts. We take u equal to t, du is equal to dt, and we take our designated dv variable and we do an integration. And I left v as 1 over k omega naught multiplied by sine k omega naught t. And dv is back to our original function. Check my work. Okay, as we go through the iterations here, we get reducing uv minus the integral of v du. As I go through this, we're going to go from 0 to 1 period, and it reduces to this for t minus your 0, and we're reduced to a final a sub k. Now the same process here will go for the b sub k coefficient. Designate the same thing, the only term that is different is you have a sine function instead of a cosine function. So this is the reduced final form that I got after my integrations. We have the period multiplied by the frequency is equal to 2 pi. So I went ahead and substituted 2 pi for everywhere there is a t multiplied by an omega naught. Here's our b sub k variable and our a sub k variable. Now, as we go and plug our known coefficients back into the Fourier series equation, we get a final form in which we can solve for in MATLAB. Hopefully that helped. Thanks.